This is myosin 5. It has two heads that can attach and release from this long protein called actin upon binding with ATP. This allows it to walk in a foot over foot motion, which is the basis of muscular contraction. But myosin is far too small for us to observe. So how do we know it moves like this? Well, we know that a step only occurs if ATP binds to its respective domain. The cellular environment is swarming with molecules whose random thermal motions cause them to collide with the binding site, so most interactions are unproductive. And even if ATP arrives, it may not collide with the correct energy or orientation to fulfill the binding conditions. What we're saying is that when a collision occurs in time delta t, it has a probability eta of causing a step. It's important to note that eta is not affected by the prior collisions. It's a function of only the current state of the system, making this what we call a Markov process. So in a given time step, either the motor moves or it doesn't. It's like a coin flip. You get heads or tails, except this would be a weighted coin flip. The chance of getting heads, a step, is eta, and the chance of getting tails, no step, is 1 minus eta. If a coin has a 3/4 chance of heads, then it must have a 1/4 chance of tails, right? Because one of those events has to happen. An event with a binary result is called a Bernoulli trial. In this case, we're asking how many Bernoulli trials have to occur before the motor takes its first step. Let's say we wait 2 trials and on the third get a step. That's saying we get 1 minus eta and 1 minus eta and finally eta, which means the total probability is 1 minus eta times 1 minus eta times eta. The hint here is that if it takes j trials for the first success to occur, then j minus 1 trials were failures. So the probability of a motor taking its first step is eta times 1 minus eta to the j minus 1 power. But remember that a trial occurs in time delta t. That's how long it takes the collision to happen, not the actual step. Since most collisions aren't productive, it can take a good couple seconds before the motor moves. That's a lot of delta t's. So rather than tracking in terms of delta t, which is a very small number, we should take the limit as it approaches 0. In an interval t, the number of units of time is t over delta t. This approaches infinity as delta t approaches 0. That makes sense. That's the definition of making time continuous. However, the total number of steps expected in that interval is eta times t over delta t, which will also go to infinity. Therefore, we need to make the probability proportional to delta t so that it drops out when we take the limit. The constant of proportionality is called the rate of the process. Now we're ready to take the limit of the whole thing. Since time becomes continuous, we don't want our unit to be the discrete counter j anymore, so we'll replace it with t sub w, the total amount of time it takes for j steps to occur. Now we have to do a little manipulation, so bear with me. This -1 exponent can be factored out as 1 minus eta to the -1. Also, we're going to multiply and divide this exponent by eta. This approaches 1 as eta gets smaller. This is the compound interest formula, whose limit is 1 over e, and this is just beta. Altogether, we see that the waiting times for a step are distributed as a decaying exponential. A 2003 study actually empirically derived this distribution by tracking myosin with a fluorescent tag. The exponential model we just derived actually fit well for a quarter of the myosin molecules. The rest had a distribution that was far from exponential. So as the whole model broken down, it seemed to the researchers that there were two stepping patterns. The ones from the bad fit seemed to take increments of 74 nanometers. The ones from the good fit seemed to alternate between long and short increments, but they summed to 74 nanometers. This difference isn't due to varying stepping patterns. It's due to where the fluorescent tag was binding to the myosin. Imagine walking around in a dark room with a flashlight and an observer watching you. If the flashlight is attached to your knee, it will move a little bit when your opposite foot takes a step, and a lot when the same foot takes a step. So the observer will see a little step and a big step. But if the flashlight is attached to your ankle, the little step is too small, so an observer could only see that big step. So the myosin molecules jumping by 74 nanometers had the tag on their quote-unquote ankle. Therefore, their step is really two consecutive steps. This means that their waiting time is actually the sum of two waiting times. The first we'll call x, which makes the second t sub w minus x. The total waiting time distribution is the sum of these two, and we get that by taking the convolution of two distributions. Evaluating this integral gives an exponential decay with an extra factor that gives that hump we were looking for.